Well, what I ended up doing was I completed the square and then did a trig sub and used one of the tables of integrals for secant the cube.
Oh, I see. So the purpose of the trig tables are at most you should have to do a U sub. If you're doing more than that, even if you use a trig table later, I'm going to have to take off some points because that's not really the point of it. You should only have to do at most a U sub to kind of get it in the right form.
Yeah,
right?
I thought it was getting kind of complicated. So it's like complete a square and then I trig sub.
Yeah, you don't have to do all that. But the real important part of that is, were you able to pick the right form based on what was given to you? Right? You have to think about, on this one, I have a lot of radicals where they have u squared and a squared in them, right? So the whole idea there was to complete the square is not a bad first start. And it's sort of like what I did here. I just did it a little bit. I didn't have to take the 4 out. You know,
yeah.
Made it a little bit easier. Yeah.
I didn't get a practice test.
Oh, you mean the
Yeah.
example test?
Yeah.
Okay. Is that the one? Okay. All right, here's a question from homework 11.3, number 34. All right, let's do this one at a time here. Sigurd Leonhard Euler. I don't know if you guys have heard that name Euler before, but he did a stupid amount of stuff. Right? Very interesting use of the word stupid as an adjective, but he did a lot of stuff. One thing he did was he actually discovered what this series, we know it converges, but he figured out what it converged to. And you can tell it's really obvious. No, it's not. What the hell? Pi squared over 6, that's the very last thing I would guess, but that's what it came out to be. And if you look it up, how would you look that up in Google? Euler's series, whatever. If any of you would even look that up. I don't know if you were interested in the proof. But that's not what this is all about, thank God. This says, use this. Euler did all the work. You're sitting next to him, you're like, oh, cool, thanks, dude. Let me use what you did to do this. Now, what's the only difference between what Euler started with and what we have? What's that again? Sorry? Starts at 2. So really, what does that mean? Which one of these, I know they both have an infinite amount of terms, but just go with me for a second. Which one of these has more terms in a way? They both have an infinite number of terms, but the first one, what term are we missing?
1.
We're missing I don't know if you mean 1 or the first one. The first term, which happens to be 1. So if this adds up to be that, this would add up to be that minus 1. Bam. How are we doing so far? Right, because I could write this to sum equals 1 plus the sum n equals 2 to infinity of 1 over n squared, right? Which equals pi squared over 6. So then this equals pi squared over 6 minus 1. All right, so that's that idea. Now this is a very important problem. I assigned this. Actually, I made sure that this was part of the assignment. I think I did. Try to. Because it deals with changing indices and changing the interior to match something else, to match the form of something else. So the next one's a little bit more difficult. Sum n equals 3 to infinity. So it sounds like it's going to be what we did just a couple more times, just one more time, but it's not. Inside it says 1 over n plus 1 squared. So I'd have students that would say, well, that's not the same. I can't use that. But real quick, if I had this, and I had to, and somebody said, no, I want to start at 0. I want to start at 0. But I want the exact same elements to come out of this. Are you with me? I want the exact same elements. So the first element here would be 1. Well, I can't have this be that. That's not going to have 1 as the first element. The first element would be undefined. Okay, that's not a good start. So what I actually put in here, so I make sure it has a 1 come out.
N plus 1.
Yeah, so this accounts for the fact that n starts lower. Then my input, that just adds 1 so that it actually comes back to what it would have been. So that's kind of the reverse of what I just did. I don't want an n plus 1 in there. I want an n. I don't want an n plus 1.
So that's just like saying n starts at 4 instead of...
Beautiful, because if I did plug a 3 in here, it would have a 4, and then I would square it. So this is the same thing as starting at 4, and the form is now the same. Let me just let that sink in. This is the kind of stuff you could do with series, because there is a lot of, not arbitrary, but there's a lot of flexibility in how you choose to represent something. And there's another way you could do it so that it starts in the same place, and there's a lot of flexibility in how you set things up. So I don't want that. I want that. There. They both would give me the exact same terms. Do you guys see that? So now I do what we did here. Exact same thing, right? Except now I just got to figure out not just the first element, but the second and the third, because that's what this is leaving out, right? So it'll be pi squared over 6 minus 1 minus 1/4 minus 1/9. Beautiful. Okay. I love that. This semester is the absence of reaction. I love it. All right. I'm going to assume that makes sense, because I don't see anybody with screwed up eyes or anything. Whoa. All right. So the third dude says, where'd he go? This one's actually a lot easier. Should be. The indices match up, right? Starts at 1, goes to infinity. I only want 1 over n squared inside, right? To use what the dude next to me did. Euler, what'd you get number 4? All right, that's somebody you want to sit next to. Well, maybe not. The guy smells that. But why is that not 1 over n squared? What else is in there? Stupid 2. Now, not really. What else is in there? Besides 1 over n squared, there's also 1 over... Beautiful. There's a 1/4, so just take the damn thing out. It's an infinite series. It's a summation. You're adding stuff up. So you can take something out of each term. So you can take that. You can rewrite this first if you want to. That's the same thing, right? And then just factor out a 1/4. GCF. And it's not even, I don't even have to really go that basic. I mean, that would become an integral if I did an infinite limit, and I know I can take constants out of an integral. I can do that because it's based on an infinite sum, which I can certainly do at GCF. Right? That's why we're allowed to take constants out and put them in to integrals. And now it's easy. Now the answer to that's going to be 1/4 the answer to that. Yeah, so pi squared over 24. Beautiful. I like that problem because, I mean, so often in here I've said, I don't know if you realize this, but very often I've said, you got to realize what you're able to do, what you're allowed to do, right? And that's one thing you're not even sure you're allowed to do yet, is how much can you play around with the indices on it and how it relates to what's inside, and you can play off of them each other. This is going to become stupid important in the next part of chapter 11. We're going to be doing a lot more of that kind of thing. Okay. That was the one question of the day. All right. It's going to be a very productive day. Yes? Oh, good. All right. Beautiful. Okay, I'm going to take this out of here. So 11 to number 12. Yeah, so you have to write the first 10 terms out. I'm going to assume you can do that. So you have to write the first 10 terms of the sequence. So that'd be A1, A2, A3 for this guy. And then you have to write the first 10 partial sums. So for example, A1 would be 49 over 10. And A2 would be
7 cubed over 100.
good. So 343 over 100. So S1's always the first term, because that's everything up until the first term. That's just the first freaking term. So that's 49 over 10. S2 is going to be that plus that. So 490 over 100 plus 343 over 100 is 833. I love it, man. That's what we're missing in this class, is this little... Yes? Sure. I was just thinking, I mean, eventually you're going to want to let go of this crap. You just tell me what it is that's a decimal, it's fine. You should notice, I mean, it starts off at 4.9 and then 8.33, so that went up by almost 4. And then it's going to go up by almost 3 and then up by almost 1. And then, you know, so the question says, does it look like the sums are converging? Very obviously the sequence converging, right? In fact, the sequence is going to... What is it going to? As n gets really, really big, the bottom overwhelms the top, so the whole thing's going to go to... And what does that mean in terms of my series? It might. It has a chance. So when I ask you, does this series converge, the first thing you do is see if it even has a chance. Is there a reason for me to do weird shit, right? So what do you check? You check to see if it's going to diverge. And it's really easy to see if it's going to diverge. If this thing doesn't go to 0, the series has no chance. So then you just say diverge and go to the next one. If it does go to 0, you go, oh crap, okay, I got to do other stuff, right? So if this would have been the other way around, very quick question, right? So you do your 10 of these, you do your 10 of these, and when you get to the 10th one, it should be around like 15 something, if I remember correctly. So yeah, your guess might be, and it starts to like 15 point something and then 15 point something, so you're like, maybe it's around 16, 15, somewhere in there. But what kind of series is this? Geometric, right? And what's R? In fact, a really good way to rewrite this so that these have the same power is to do what up here? Take a 7 out. How many 7s are there? N plus 1 of them. You want only N of them there so you can kind of put it together with the 10. So take 7 away from it. So it'll be 7 times 7 to the n. So I can write that as the sum 7 times 7 over 10 to the n. You guys with me? Alright, so now I know what R is. And it's less than 1, so that's another way I could have said it's converges because it's a geometric series with R less than 1.
How do you know when you take out the 7, you don't put it outside of this?
You could. I could have. I just didn't. I don't know why. I could have totally put it out there. So for the sum of an infinitely... Now let's try this again. For a geometric series, what's the infinite sum of a geometric series? It's a nice little expression for that. Whoa, okay. I think it's that. See if I remember that correctly. A is the first term. And the thing to be careful about here is it starts at 1, right? N equals 1. If it started at 0, it'd be easy. The first term would be that extra 7. Because then this to the 0 would be 1. But it starts at 1. Damn, so what's the first term? Well, we know what the first term is. I already wrote it down. 49 over 10. Huh? So the first term is definitely 49 over 10, right?
Yeah.
That's the first term. And then R is 7/10. So you get 49 divided by 3, multiply that bottom by 10. 49 divided by 3 is just over 16. 3 goes into 48 16 times. So your guess, it's about 15, 16 is perfect. If that would be your guess. Maybe. So remember this, the geometric series is in this section. The sum is on page 706 for geometric series. We don't get this thing all the time. I mean, look at the weirdness we just did a minute ago. That Euler did. I mean, that took him a long time to do, to figure that out. There's no set form of doing that. You have to attack it on its own. It's insane. We don't get this kind of thing often. Or it's a closed form. I just got to plug stuff in and I know what the sum is. I don't get that kind of thing often for infinite sums. Okay. Maybe yes.
Number 36 in this section.
Oh, okay. That definitely looks freaky. So 36 in the same section. So the question here is it convergent or divergent? If it's convergent, find its sum. So I don't want to give it away. Let's see. Somebody have a suggestion on how to attack this thing?
Well, the bottom, the 2/3 that m is that it means larger, it's just going to get smaller.
Good. All right. Because again, now I'll give it away now. Try not to break it to salt. The first thing you always do, if I ask you if a series converges or diverges, is the test for divergence. That's the easiest, quickest answer. Please don't just pass that by and start doing weird stuff, multiplying by 2/3 the n or something weird. As you let n go to infinity, what happens to this part? Goes to 0. So what's the whole thing go to? That sequence goes to 1. Does that series have a chance to converge? In order for it to have a chance, the limit has to be 0. So the limit of that is 1. Does the series have a chance to converge? No. So the series is next. Right? Done. You with me? That's what you always try first, because maybe the sequence that's in here, that the series is built on, doesn't even go to 0. Then the series doesn't have a chance to converge. Okay, cool. Yes? Oh. 11:1, you said? So when A1 equals 2. Like that? Okay. So in general, if I give you a recursively defined sequence, and that word recursive means it just kind of builds on itself. the next element is dependent on the element before. And most sequences are. It's just that when I define it recursively, I am explicitly telling you what that relationship is. Stop right there, you guys. So you can see that element in general is exactly dependent on the two before it, like this. So if you, I know what A1 and A2 is, so figuring out A2 here wouldn't make any sense, because then one of these wouldn't even be 0, it would just be empty space. Right? And I have no idea what 1 minus empty space is. So I'm going to start here with A3, and in order to make A3, n has to be 2. So I'm going to do A sub 3, so this is n equals 2, equals A2 minus A1. So if you're very explicit to yourself as to what those subscripts are, you know exactly what to plug where. Are we good so far?
Yeah.
Cool. So then A2 was 1 and A1, so A3 is negative 1. And then so the same way A4 would be n is 3. So that would equal A3 minus A2. So A3 is negative 1. Minus A2 is 1, and so forth. You might want to at least circle these bad boys down as you go. And however many the more they want from you, just keep going the same way. Just subtract the 2 before. That's sort of like an inverse of Fibonacci, right? Because Fibonacci is add the 2 before to get somewhere. This one doesn't really do much interesting stuff. Yeah.
Can we do 3 from the example test?
Yeah. Bless you. Okay. All right. So this says determine if the sequence converges. If so, find the limit. And the funny thing is, in the process of determining whether or not it converges, you pretty much are going to find the limit. Because I can't immediately see much of anything here. I don't know if you guys see that. I mean, if n goes to infinity, the inside becomes beautiful. It becomes an indeterminate form. In which case, I could do L'Hopital's or something maybe even easier than that, if only the limit was being applied to that. And why am I allowed to? So the real question is this limit something? And of course, the tangent's in my way, but is it?
Can you use L'Hopital's when it's inside?
Well, we're getting there. When I have the limit of a continuous function of something, I'm allowed to take the limit inside. And then you are doing the limit of that rational function. Right? So I can just bring this inside. So now it's the tangent sitting on the outside waiting. And inside I've got the limit of this thing. So it's really like that's my first problem. So I'm completely allowed to do L'Hopital's. Why do I not really have to do L'Hopital's? Why do I have to do Because that's just what's the yeah exactly. I think that's what you guys said. The degrees. What degrees on the top and the bottom are the same? So you just have to have the ratio, and the variable here, of course, is n. So what's the ratios? Yeah, negative. Not quite. Don't forget a little pi, dude. So this limit. Ooh, yeah, we're gonna. So tangent of 2 pi over negative 6, so negative pi over 3. You stop right there. Does everybody see where that came from? Once you bring that limit inside, because tangent is continuous on its domain. If you have a function that's continuous on its domain, you're allowed to bring the limit inside. You guys do it without even thinking about it. If I said the limit as x goes to 2 of square root of x plus 3, what would you do? Uh-oh. All right. Well, shoot. I've uncovered something I didn't want to know. Well, what's the answer? Don't overthink it. Square root of 5, right? But you just did what we just did. You brought this limit inside of a continuous function. Square root's continuous on its domain. You don't even think about it like that, though. You just plug the damn thing in. So that's really what we're doing here. Just with infinities, you have to be a little more explicit. In tangents, we're not used to doing that kind of thing with. And what is the tangent of negative pi over 3? Almost negative root, because we're in the fourth quadrant. Yes, we're in the fourth quadrant. Right? Down 60 degrees. Yeah. Oh, scheisse. So at any instant on a test, you could be faced with that. And I do not want a decimal answer if I give you a trig function of a value you should know. Right? So if somewhere on the test it says sine of 120 degrees, I don't want to see any freaking decimal crap. I want to see the exact answer. Right? So some of you guys are like, oh shit, I got to go back and remember my trig. It should be like, bam, in your head like crazy now. Should be. Okay. So anything else from, yeah?
Number 5, A.
Oh. On the one I just gave out? Oh, yeah. This is old. All right, so the funny thing about the idea we just used to figure out the limit of the interior of the tangent, I can actually use the exact same idea here in a way. I have to be a little careful. In fact, we should probably apply L'Hopital's because of the 3 inside. But I already kind of know that the limit, in order to answer the question, is this series convergent or divergent? What do I do again? Very first thing? Make sure that the sequence goes to 0. If it doesn't go to 0, it's quick. I'm done. It's divergent. There's no chance. So does the sequence go to 0? No. Yeah. So if you really, really, really want to show it, and you do, I can apply what? L'Hopital's, right? And actually, I mean, just to cut to the chase, you could do the same. You don't have to do L'Hopital's, but let's just do it just because. So what would you get? Minus 3.5 over 2 n to the negative 1/2, right? Is that cool? It's the negative 1/2 is 1/2 times n to the negative 1/2, so that's 1/2 of that. Right. And why is that 3 to the 1/2 power? Because it was inside the root 2, right? You can't just take it as a 3. So what happens to the n to the negative 1/2? They cancel because they're both there. And the over 2's cancel. So if you really wanted to know for sure, this limit is 1 over 3 to the 1/2. Yeah. What's most important about that is that limit is not, it's not 0. Divergent. Didn't even have a chance. Poor little dude. If I would have made that, let's say, if I would have made that one a 4th root, How do you think it would have been different? The degree would have been bigger on the bottom, because a 1/2 degree is definitely bigger than a 1/4 degree, right? So then it would have gone to 0, then I would have had to do something further. How would we do it? Comparison test probably. Yeah. Because, yeah, I really... Huh? Sure, maybe not that one. But real quick, I mean, if you have n to the 1/4 minus who cares over who cares n to the 1/2, right? The who cares stuff doesn't really matter. That reduces to what? 1 over... Well, that's n to the 1/4 over n to the 2/4. 1/4 minus 2/4 is... 1/4 minus 2/4 is 1/4, right? Negative 1/4, so it'll be that. And what would that do? 1 over n to the 1/4. Would that series converge or diverge? Why? Why does it diverge? Yeah, the power, in order for it to converge, this has to be bigger than 1. It ain't. And so what kind of a series is that? What kind of a series, I'm sorry? P series. Right, that's when you have something like this. That's a P series. If P is greater than 1, this converges. Otherwise, it diverges. We've seen that a few times. It's popped up a few different ways over chapter 11, yeah.
So how did we get the n to the 1/4?
So this is the thought process, because the rest of this stuff doesn't matter, right? This is the thought process to help you figure out if it is going to converge or diverge. And if you're going to do a comparison test, the route you go totally depends on, do you think it's going to converge or diverge? If I thought it was going to converge, I want to find a series that is bigger or smaller than me. Bigger, because I want it to be my ceiling, right? If I think mine converges, I want to find a series that's bigger than me, that converges. That's my ceiling. If I think that diverges, which I do, I would find a sequence that is smaller so that it's series, and show that it diverges and it pushes me to infinity. I also have to diverge. So it's all about, I'm just trying to show you a little bit of this is nowhere near enough to prove a damn thing, but it's enough to give you a feeling, is it going to do this or is it going to do that? Because if you think the wrong thing, you're going to be trying the wrong thing, it ain't never going to work. Right? You've got to have some kind of feeling going in about what it's doing. So, let's see. Do we have a nice... What about... If I had something like this here. I guess that wasn't really that bad of a sequence. Believe it or not. Yeah, let's do that same sequence almost. So based on what we just did, do we think that's going to converge or diverge? We think it's going to diverge, right? Let me think. Well, do I have this set up the right way? Yes, good. So what's the limit as n goes to infinity of this? Which one's growing faster, the top or the bottom? A fourth root or a square root's going to grow bigger? The bottom's going to... So this does go to 0, so it has a chance. Otherwise, I wouldn't do anything, right? I wouldn't do this stuff if it didn't have a chance. So it does have a chance. The limit of this... Got it. Limit of that is 0, has a chance. Right? Which for us is bad news. That there's hope for this thing. It's bad news because it means we've got to do more. If it didn't have a chance, we could stop. For like really lazy doctors. So I want to compare this to, if I feel like it diverges, and I feel like it diverges because of this thought process here. Right? If you left the fourth root on the bottom, that's definitely going to diverge according to the p-series. So if I could just make this, so I want my series, let me refer to this as the sequence inside the series. I want that sequence, I want to find a sequence that is bigger, smaller, because I want it to push me to infinity. I want it to be the floor pushing me to infinity, right? If I think I converge, I want a series to act like my ceiling that converges. If I think it diverges, I want somebody to push me to infinity. A smaller sequence that diverges. Do you guys say again?
Could you put an N on the bottom?
Okay, let's go in that direction. So, we sort of did a little bit of this the other day, where I was replacing stuff with something that would maintain the inequality. I want to find something that is smaller than this, where the limit as n goes to infinity of Bn is infinity, is diverges. So if that guy diverges, my guy definitely would be shown to diverge. Right? So if I start with this, I want any inequalities to be greater than as I move along, right? So this is where you could do so much more than you ever thought you could, because it's a freaking inequality. So what I really want to do is to somehow make these become irrelevant, either by making them zero or by making them like terms with this so that I can just put them together. I don't know if you guys get that. That's really almost the heart of any of this that we do. So, for example, to make this become smaller, I'd want to divide by more than I currently am. Is that understood?
Yeah.
So what's the quickest way to make the bottom bigger than it is currently?
Give the 3.
Is just to make that go away. Then I am definitely getting a sequence that's smaller. The bottom's bigger, so the whole thing is smaller. So if I just do that one thing, if I do that, bam. That sequence is smaller than this sequence. Now, can I just take the -1 away? If I do that, I actually make it become, oh, it's not the right goddamn way. So people get really confused. Everything you do has got to make something that is smaller than what you're currently looking at. So if I can't make that just go away, what could I do? And this is maybe, I could have done one thing that would have made this a lot easier, but I didn't, so it's too bad for all of us. If I would have put a 2 there, this would have been a lot easier. But I don't need it there for it to work. So what I can do then is I can say that this is bigger than, let's see, I don't want to put an n to the 1/4 on the top, because then it's 0, and what good does that do me? I want to put minus something that is like terms with that. N's not like terms with that. So let me just give it to you. Now, real quick, hold on. That's not always true, right? If n is 1, that's 1/2. You with me? But at some point, that is true, right? If n is 16, this is 1. So starting at n equals 16, this is true. And all you need is for it to be true eventually. And this is the freaky part about this thing. Whatever the first parts of my elements do, whatever they do, they can't make infinity. I can ignore as much of my series as I want to, until eventually it starts doing what I want. It's sort of like related to the integral test, where they said you could, it has to be decreasing eventually. So at some point it's got to be decreasing forever, but that could be at the 4th element, the 12th element, at the 18 trillionth element, right? Because any finite series of terms, could it ever make infinity on its own? Any finite series of terms, could you add them up and get infinity? Hell no, right? You'd have to have one of them be infinity. I'm not talking about that. Any finite series of terms could never make infinity. So at 16, this is true, and that's all I care. It's true forever after that, isn't it? Because after 16, I'm subtracting something more than 1 away from this. That's definitely smaller than what it was. So what's good about that? What's a whole of this minus half of this? So I get 1/2 n to the 1/4 over n to the 1/2, which reduces to 1 over 2, what we just did here, and the 1/4. That's what I tried. So the idea is to just freaking get rid of these stupid numbers. The bottom was easy. I could just get rid of it because it made my inequality the way I wanted it to be. I can't just if that would have been a +1, that would have been so nice, Jeff. Right? But I was an asshole. I didn't do it. You can't just get rid of it because it actually makes the inequality the wrong way. Your comparison test won't be valid then. You can't be certain that what you end up with is actually smaller than what you started with. So I had to actually make it get bigger. And actually like terms of what's there so that I'm able to do this last step, which is reduce my end stuff. Okay, maybe. So I'm not going to do anything excessively freaky to you in this regard, but this is really important for the rest of chapter 11. A lot of it's going to involve, well, not a lot of it. Some of it will be these comparison tests, and we have to get better and better at doing this kind of thing. Now, real quick, I just want to make this point real quick. If I would have made that 2, then we would have been, I would have done this thing first, exactly like we did here, right? And then I could have made this is greater than 2n to the 1/4 minus n to the 1/4. That would have been easy, and that's true always. Because n starts at 1, and that would have been equal. It's got to be at least equal, if not less than, or at most equal, if not less than. Right, so that would have been a lot easier to kind of stomach, but I didn't think that far ahead when I made that problem. So I just did the exact same idea. I took, why is this minus 1 of these, so that it actually has something left over at the end. So I couldn't make this minus 1, I had to make it minus anything smaller than 1. 1/2 is the easiest next thing. Maybe. So again, that's enough of that. That's not going to be anywhere near dominant on the test. But it will be on there somewhere. I had to get my creepy evil voice.
Secret problem is being done in the back.
That's nice.
The back of one page. It's like
It goes around the test in in 1-point font. Yeah.
you like peel the paper in half and find it on the inside of the paper.
They'll give me ideas. So, yes.
Number 1.
Oh yeah. Okay. I like that problem. Has everybody got what they want from there? More than you wanted? Now, yeah, and number 1, there's a couple of evil things there. Notice, by the way, real quick, I didn't have a lot of time to do this earlier, but we will have questions about integrals tables, right? So I'll give you a selection just like I did on the quiz. And we will have one question about like a trapezoidal rule or something, a Simpson's rule. It was not going to be, it can't be that extensive, obviously, right? Because those, if I did a couple of those from homework, it might take the whole time. But I'll give you the rule that you need. It'll be up there on the test for you. So 2 evil things about this, really.
3.
Yeah, I can't use 3. I can use 3, I just can't. There are, what was evil about this, Jeff? Yeah, okay. This is going to mess me up a little bit later, so you got to be careful about that, right? But there is a nice, neat thing. You don't have to use trig sub on this, unless you really want to. So, very first thing I got to do is,
Set t to 3.
yeah, limit t goes to 3 from
The right.
Now, any suggestions on how to handle the actual interval itself? Beautiful idea. Let u equal x squared minus 9. It's a good start.
Why the x squared and not the x cubed?
Two things. The only other part, if I'm going to use u sub, the stuff that I don't let u equal has to be the stuff that's going to go with dx to make du. And there's no way this stuff can get up there.
Okay.
You see, so I could never let, I wish, because then x squared, yeah, is the derivative, but that x squared can't go with the dx, so that can't possibly work. So I want to nip that in the bud right there. You have to let u equal x squared minus 9, truly, if you want to use u sub. And then du is?
2x squared.
And what saves your ass, because that's not, there's 2x dx, but then you have an extra. And the fact that it's an extra x squared should be enough of a hint. What did I do there? Du. So if u is x squared minus 9, x squared is u plus 9. So with this, and with this, and with this, we cover everything in there, right? So I get limit t goes to 3 from above, t 5. And be really careful, guys. I mean, if you want to do like I do it all the way like I do. Those parentheses tell me I can't just plug those in for u. This is what x does, not what u does. So at the end, I got to bring x back in before I plug those in. So 2x dx is du. The x squared left over is u plus 9. And the square root of that is square root of u. Now, do you see the usefulness of having done that? What does that do for me? The bottom is just, it's just one term, so I can break it up. See, so a lot of the tricky u sub stuff involves taking something that's not truly one term on the bottom and making it one term, and then just making everything else work according to your pick for u. So now I can break that up, go from there. Is that cool? So this would be the limit. T goes to 3 from above, integral t to 5. U over u to the 1/2 is? No. A whole u divided by half of u leaves you with the other half of the u, right? So u to the 1/2. Plus 9. U to negative 1/2, and that's easy to integrate, right? Right. Easy to integrate, right? So what do you get when you integrate this?
3/2 divided by.
Yeah, u to the 3/2 times 2/3, and u was x squared minus 9. Let me bring this up here. So I've got limits. T goes to 3 of 2/3 x squared minus 9 to the 3/2 plus 9 over 1/2, which is 18. U to the 1/2, right? And u, of course, is from t to 5. Yes, sir.
How does x cubed equal u plus 9?
It doesn't. I never claimed that. So up here I've got 2x cubed dx. Is that cool? Because the bottom's easy, right? Because the bottom just be square root of u. So 2x cubed dx, that's x squared times 2x dx. Is that cool? 2x dx is du. X squared is u plus 9. So part of it gets sucked in with the du, and the rest of it is the rewrite for the u that I did. All right, cool. Cool. And now you just got to plug in. Oh, goodness gracious. So when you plug in 5, you get 16, 4 cubed, right? So 5 would be 25 minus 9 is 16. Square root of 16 is 4 to the third power. It's 64. So you get 128 thirds. Let's plug in a 5 in. Plus, same kind of thing happens. 25 minus 9 is 16. Square root is 4 times 18 is something. 72, yep. And minus, plug a t in. And what's going to happen when I let t go to 3? Yeah, they're both going to be 0, right? So I'm okay with you going, okay, that's 0, that goes to 0, that goes to 0. No problem. I mean, that's nice and quick. The original problem with 3 was because the square root of that was on the bottom, but after integrating, the square root effectively comes up. In this case, it comes to 3 half power. All that matters is they're both up, so there's no problem at 3 at the end. So it's just both of those go to 0, so then my answer would just be whatever the hell that is. .344 over 3. Sounds about right. Cool. I like that problem. And you should have, in your homework, you should have hit some of these improper integrals where you had to do some by parts. You had to do some u sub, obviously, and so forth. So it could be an improper integral where it requires a trig sub or it requires by parts, depending on how evil I feel when I make it. Okay. In section, which section? 24. Oh, yeah, good. All right. So everybody got what they want there? Okay. All right. So this one. So you just get a feel for this thing. When x gets really big, 3 doesn't mean crap, and that reduces to what?
I didn't know what to do.
Okay, don't answer my question. How do you write e to the 2x? E to the x all squared. So e to the x over e to the x squared reduces to 1 over e to the x. And I want you to realize how what we're doing with series actually kind of changes how you look at integrals. This is really what this is asking, right? Yeah, that's right. 1 over e to the x, if that was in a series, what do you think it would do? Would it converge or diverge? Why would it converge for sure? No question. I mean, 1 over n squared would, summation of 1 over n squared would totally converge because it's greater than 1 power. E to the freaking n grows a lot faster than n squared. So if 1 over n squared converges, e to the n freaking converges like crazy. So just knowing that this is roughly 1 over e to the x, I know this interval is going to converge. That doesn't tell me the answer, but I know it's going to converge. Right? Okay, good. So now let's figure this out. So who's got a suggestion, realizing that that's actually e to the x squared? Yeah, u sub. So u equals e to the x. Craziness. Okay, so now I get integral 0 to infinity. Oh, I might as well choose my limit c to infinity This will be u over u squared plus 3. And what's that? So are we good so far? Are we good up to this point?
Just 1/2 and then u2 plus
It will. And right now, before I forget, this will become an ln. It will. And it will be just an m sub, I'll call it, because we already did u sub. So one more level of sub. This is, the inception kind of interval. dm would be 2u, right? So then I just need to introduce 1/2 out there. So it will become ln, because it will be the integral of 1 over m. Do you guys see that? Yes, sir.
Since du is e dx, dx, shouldn't one of those e dx's go into du? Shouldn't it be 1 over u squared?
Oh, right here. Yeah. Okay, good. I don't know why I thought I had more up there. All right, that's even better. Let's feed into this. So, my mistake, I put a u there. I really shouldn't have, because e to the x dx is du. It's this guy that I had to put u in place of. So if it would have been this, it would have eventually become a natural log, because they do end up with 1 over m. And the only thing that becomes natural log is if I have 1 over a linear function of the variable. So this really shouldn't have this u there. Should have a 1. So what am I going to have to do with that? You could either realize it's going to be arc tangent, right? Or you can do the trig sub that's going to get you to arc tangent. But the bigger problem I have is I'm seeing way too much of this kind of thing. In fact, I'm seeing some really scary stuff. I'm seeing stuff like, x cubed plus 7. Well, that's obviously just natural log of x cubed plus 7. I don't know what people talk about, why this calculus stuff is hard. Hell no. If you do this derivative, it's 1 over that times the derivative of that. The derivative that's missing. Which is why if there were a u, it would work. Because ln of that, the derivative would be 1 over that times the derivative of that, and it would be there. That's why it could be ln. So see, way too many ln's just everywhere. Right?
LNs, no.
Yeah, exactly. So no good. I'm also seeing something that's even scarier in a way, and that's when I see like integrals, let's say x sine x. And that becomes x squared over 2 cosine x, negative maybe. They get the negative right. But, I mean, I have no problem, and I don't care if you think this means bad things about me as a teacher, I have no problem pointing out and saying that is just bad. That is bad. We should be beyond this problem. We should be beyond this error. But I see this a lot. What's wrong with that? Is there something wrong with that? Am I just making another mistake?
By parts,
I'd have to do by parts. Integrals don't have a product rule. And if they did, it wouldn't just be integral of each piece. The derivative, I think I've talked about this before, but I'm still seeing it. The derivative is harder to do than just the derivative of each piece. You have to do one, and then the other one gets a turn. So the integral would be nowhere near that easy. We know it's nowhere near that easy. All right. So here, this, if you realize it is just going to be arctangent or inverse tangent of. And this is where you got to be careful with the 3. If there is a 1 there, so if you look at the, or if we want to do trig sub, so if you look on the table of integrals, reference page 6, a squared plus u squared. So it'll be 1 over square root of 3, u over square root of 3, right? So it's, forget my little limit. This is from t to, 0 to t. So now I can throw back in here what u is and throw my
It says on the
Well, but a squared is 3. Yeah. What happens to inverse tangent if you let its input go to infinity? Who remembers? Beautiful. Tangents contain between negative pi over 2, pi over 2 this way. So inverse tangents contain between them and outputs. So as it goes to infinity, the outputs goes towards pi over 2. So when you plug in t, so u was e to the x. When you plug in t and let it go to infinity, that part's going to become pi over 2 there. So 1 over root 3 inverse tangent of e to the t over root 3 minus 1 over root 3. What's the inverse tangent of, well, if you let it be 0, e to the 0 is 1. Inverse tangent of 1 over root 3. Yeah, why is it pi over 6? Well, just because it's how you remember it, right? Always, well, I'll let you guys, however you have it memorized, keep it that way. I won't tell you how you do. So this will be, where did I go? Okay, so here, if I let t go to infinity, what happens? We just talked about that. That piece goes to pi over 2. And of course, that is going to be pi over 6. And then you just clean it up a little bit. Okay. Anything else from anywhere? Yeah, I like 5B. Let's see. So with 5B, what is that basically trying to be, this series? What kind of series does that sort of look like it's trying to be? Geometric, right? And even better than that, it's kind of weird for me to say that series because this really is... there's no way to say this without just giving it away. It's 2 series slapped together, right? It's the difference of 2 series. Totally break it up like that. So one of the first things I could do is say, okay, this is sum n equals 1 to infinity, 1 over phi to the n minus 4n plus 2 over phi to the n. That's equivalent to, if I had a whole bunch of stuff to add up and some of them were positive and some of them were negative, couldn't I add up all the positive, add up all the negative, and then subtract them? If you had a long list of numbers, right? That's all we did, right? Bless you. And now I can treat each of them as its own geometric sequence that it is. What little cleanup do I have to do on each one of them? What's R here? 1/5. And if I did that, did I change anything? If I put an n there?
No.
I didn't change a damn thing. Good. Is 1 to the n, where n starts, 1 to any power is 1. So R is definitely 1/5. So I can do that thing on it, right? The S equals A over 1 minus R thing. And to answer the first question, of course, this definitely looks like it's going to be convergent or divergent. Because R here was 1/5, which is less than 1. R here is going to be 4/5, which is less than 1, so it's convergent. So this looks like it's going to be convergent. So this converges to a number, that converges to a number, and when I take the difference, that's not something you're going to make an infinity. 7 minus 5 is infinity. No. What do I have to do? A little cleanup here. Yeah, one thing I could do, it doesn't really matter. It really doesn't matter. But you could take the 16 out so you can see the 4/5 to the n. But to tell you honestly, for this dude, all I got to know is the first term and what R is. right? And I can see what R is. It's going to be 4/5. So here R is 1/5. Here R is 4/5. What's A here? 1/5. Good. And what's A here? N equal 1. It'll be, if you let N equal 1, it'll be 4 cubed over 5. A is always the first term, and how do you always find the first term for a series? You let N equal where it starts. That's the first term. So if only this would have been 0, that would have been a little bit nicer, but too bad for us. It wasn't. Okay? And so this piece is going to converge to what? S equals 1/5 over 1 minus 1/5. And what's that? Multiply top and bottom by 5, makes it easy, right? 1 over 5 minus 1, so 1/4. This one is going to be 64/5 over 1 minus 4/5. So again, multiply top and bottom by 5. You get 64 over 5 minus 4, so you get 64. So the whole thing converges to 64 and 1/4. I'm sorry. Let me slow down. I want to subtract these two. So it'll be 1/4 minus 64. So that's going to be, yeah, it'll be, yeah, sure. Negative 63 and 3/4, something like that. Good. But you could do that kind of thing with a series. You can break it up, because a series and an integral are very much related. I can totally break an integral across a subtraction, of course, right? So I can do the exact same thing with a series. Now be careful, they're not the same thing, but they're related enough that they have a lot of the same properties. Yes?
For the second part, the 4 to the n plus 2, how come you don't have to make the bottom n plus 2 also?
Oh, to use this, all I need to know is what the first term is and what the repeated ratio, the ratio is between two, the multiplier.
So it doesn't really matter as long as it's raised.
Yeah, so if you wanted to, you could write this a little bit more, you can take this 16 out and then make this 4/5 to the end. But it doesn't change what the first term is, and it doesn't change what the R is. Yeah. As long as you can identify those two things, you can apply this. Cool. Yeah.
I remember you saying something about when for your summation, when n equals 1, your r to the n needs to be r to the n minus 1. I remember you saying something about.
Well, it was when I was trying to prove the partial sum formula using math induction, or not in math induction. Sorry, it was when I multiplied by r. I don't know if you remember that. And I started with the wrong exponent, so it wasn't coming out the way I knew it should. And it's because it would started at 1. So when it starts at 0, it could just be an n power on there and be fine. But if it starts at 1, and that's really when I give you a sequence. If I give you a sequence that's geometric in nature, like 3, 6, 12, 24. So I can't just say that that's going to be 3 times 2 to the n. If it starts at 1, that's not true. Because the first element's supposed to be 3, but this would be, the first element would be 6, and that's why I would need the minus 1. So it's only when you're going this way that kind of comes into play. If it's given to me, I don't have to worry about any of this. Somebody else already worried about it for me. I just have to identify the major parts. But it's when you're going this way that you have to be careful how you write it. And I wrote it with an nth power. It should have been n minus 1. Yeah. Or something like that. It's, powers didn't match up the way they're supposed to. So, make sure anything else on this thing you want to take a look at, because I didn't get an answer key for you. Oh yeah, okay. Number 6. So you guys try that one yet? I highly recommend you try that one right now. Number 6 on the example test. This isn't overly crazy difficult. Oh, thank you. But it is just interesting enough. So there is one thing missing from the first element that doesn't match the form, but it's not missing because of what it would be. So if you kind of go backwards, square root of 4, square root of 3, square root of 2, there should be a, and of course there is, because it's just freaking 1, right? So that's the kind of thing to be careful about. Don't let that kind of thing mess you up. Just realize it's not there because it didn't have to be there. But you can put it there so now you can see the form better, that it does go across. So A1 is this, A2 is that. And part of your main concern when you're trying to write it from list form into summation form is what's going to be n plus 1, what's going to be n plus 2, what's going to be n minus 1, that kind of thing. So the radical parts are following exactly along with my series as long as they start at 1, right? Just be a good place to start at 1. You can start at 10, I don't care. So if I start at 1, what does this thing start to look like? The square root would just be the square root of n. And this guy would be n plus 1. Kick ass. Of course, this should not be that difficult of a question about convergent or divergent either. What should this do? Why? It's not good enough. So is 1 over n. So this is a series. Not just does the sequence converge. Beautiful. That's it. That's the key. Right? So 1 over n is true for what you said first, and that doesn't converge. The point is this is a p. You could look at this as a p series. And when you first look at this, you don't think that that's what's going on here, but it is just basically n times n to the 1/2. Now what can I do to my series so I don't have to do a comparison to, well, you still would, because then that would screw that guy up. It's too bad for you. But this is basically 1 over n times n to the 1/2, which is 1 over n to the 3/2, and that is totally convergent because its power is bigger than 1. B series.
Can that be why or why not? Because it's greater than 1.
Yeah, and I'm on two minds of that. I would say in the instructions, if I wanted more, like use a comparison test. So, but again, my brain remembers when I was a student. If that was an n, whatever's true for that is definitely true for this being an n plus 1. I mean, that's all there's to it. You're making the bottom even a little bigger. It's actually getting to 0 faster than it would have been. So, but that's exactly the comparison test, isn't it? So if I wanted to use a comparison test on this, I know it converges. So I want to find a sequence that is bigger to act as my ceiling, right? Somehow it's going to get stuck in your head. You got to figure that out. So I want a series that's bigger than this, and of course, that's really simple. How do you make a series that's bigger? I don't want to divide by as much then, right? So then I just make it that. If I make that n, isn't that going to be bigger, the result? Because I'm dividing by less. So that's like a one-step comparison test. Bam. Right here you can say converges. You can say converges P series. That'd be awesome. You get a little reason. That's all you got to say is P series. That's all you got to say. Kick ass.
So would it be wrong if we said that it converges because it goes to 0? Or is that not enough?
So two things. What goes to 0?
Well, because the bottom is really
No. What goes to 0? The sequence goes to 0. Which means the series might converge. So you got to be really careful. the limit of the sequence is 0 for sure. But the series, I don't know. But now that I know it's a P series, where P is bigger than 1, then I know it's convergent. I have to do more. So say that's a perfect example. This sequence goes to 0. It might. I've got to then do more to show that it does. Since it's not on the order of 1 over n, that would diverge. It's better than that. The bottom is bigger quicker. So it gets out of its own way better. Okay, maybe. I love it. Some of you guys look like, if I bang my head on the board, will that help? Will it get in my head? Let me try. No, that didn't help. If I sleep with my book, will that help? That's totally up to what you do with your own time. Don't recommend it.
Just like play all the tutorial videos while you're sleeping. See
Yeah,
if
sure,
it
that would help, right?
See if it somehow seeps into your head when you wake up and you have like n+1 floating in the back of your head. You're like, what does it mean?
Oh man, I remember that Dexter's Lab where he had the French going, and he said all I could say was, "What was it, omelette du fromage or something?" Right, Dexter's Lab. Yeah.
For 2 on the practice test, is that kind of like a trick question because no value of sine would be over 1. So
There you go. That's it. I love it. So number 2, I was expecting a question on that, but maybe it was too easy. Number 2, the power on n would have to be bigger than 1, but the output for sine is at most 1. So is there any value of theta that would make that converge? Hell no. The best it could do is 1 over n. That's the closest it can get, and that's not good enough. P is not bigger than 1. So no, it's always going to diverge. Kick ass. I like that. So people did, when I gave this test, I got a lot of weirdness. And that's all I had to do is realize it's a P series, that sine theta is a number, and that number can never be what it's supposed to be to converge. So it's going to diverge. That's great. If we do number 4, that would be all of them. That's crazy. So, how would you show that number 4 is non-increasing? Non-increasing is another way of saying what? No, not really. Decreasing implies that it's never the same. So non-increasing is sort of like saying the difference between negative and non-positive. Negative doesn't include 0, non-positive does. So it's really the same thing. 0 here would be no change. It could stay the same. So non-increasing, how to show that? Yeah, one way you could actually do math induction if you wanted to. Or you could just take a derivative and show that that is negative, right? That would show that it's non-increasing. Or that sometimes it's 0, but it's never positive.
how is it negative? How is it negative?
Let's see. Let's take the derivative. Well, what's the first element term? Real quick, what's the first element? Yeah, so it's 5. Right? And that's going to converge to 2/5. I agree with you. So that means it sort of makes sense that it's going to be decreasing, not increasing. Yeah. But let's see. Real quick, how do you take this guy's derivative? Quotient rule, right? And you got the whole song, or the song I sang to my calc students was top first. And that's it. I'm not big into songs. Right? I hated the freaking song because it rhymes 2 different ways, and high D low, low D high. How do you know for sure which one's first? Screw all that crap. Top first. So the derivative top is 2 times the bottom, minus because the bottom is to a negative 1 power, so a negative would come down in the derivative. So when I do the bottom's derivative, that term is minus because it's to a negative power, isn't it? 5n minus 4 to the negative 1. That's why it's in the bottom. So now the whole freaking rule just makes sense. I don't need a song. Sorry. Whenever I say that, I feel like a really crotchety old man, but you bet. That really made it sound worse. Derivative of the bottom is 5 times the top over the bottom squared, which doesn't mean a damn thing. That's always positive, right? As long as n is bigger than, not equal to 4/5. And then it's not going to be 4/5 because n starts at 1. There you go. See, so the only problem spot is not even going to be. So I get 10n minus 10n is gone. I get negative 8 minus 15 is negative 23. So that's always... It's always negative. Good. So it's even better than non-increasing. It's straight all decreasing, Jeff. Why did I even say that? I don't remember. It's been 4 years since I made that. So that shows very quickly derivatives should be easy sell, right? No matter what the hell it is, almost. So that shows very quickly it's always a negative slope. So it's definitely decreasing. If we also know that it's bounded below, and obviously we do know it's bounded below, what could you conclude about this sequence? If you know it's non-increasing and it's bounded below, it must converge. And then I always have people say, well, what if it doesn't even get close to the bound? What if it's just up? Well, then it converges up here. It converges somewhere in there, right? It's got to converge somewhere, period. Either it stops moving or it doesn't stop moving and it converges there. Okay, good. So you better believe I'm probably going to make a problem where you almost have to take the derivative to show that it's doing increasing or decreasing.
To show that it's increasing, would the derivative have to be positive?
And to be honest, again, it just has to be increasing or decreasing eventually. So you could actually take the derivative and it's positive until a certain number, but then you just are going to show it's negative forever after that, and then you could say it's decreasing.
Is the test going to be this long?
No. It's going to be longer. I cut out a few things that didn't really, because this test had some stuff from the next couple sections on it, so I cut those parts out. I would hope that you'd have no problem with this length of a test. So of course, just to make it so that somebody have a problem, I got to make it longer. No, I'm joking. Come on. It's not going to cover enough stuff because we also have to throw in there the tables. I've got to throw in there trapezoidal rule or something like that. So it's going to be at least 2 more problems on there beyond that. Something else from homework or practice test or study guide thing or? I really don't mind leaving early because I have a 2 o'clock meeting to get ready for. Yeah.
I have a kind of weird question. From the last test, I went to do my test corrections and asked the tutors how to do it. And none of them could do it. And it's the fourth square root of x.
Oh yeah.
Can we do that one?
I'm upset about that they couldn't do that problem.
I asked like 4 or 5 different tutors.
Of course, some of you guys are like, well, that's just evidence that Jeff's a jagger. That just means the tutors need some more guidance. Well, plus we did a problem a lot like that problem. Was it the practice test or something? So that's why I felt even more comfortable just giving you a problem like that. But in general, this is not immediately going to have something to do with that problem. But real quick, if I had something like this, not even that, there was a problem sort of like this on a test, on a something, or I can't remember where it was. And you had to do the integral. Do you remember the idea behind this one? X to the 4th is x squared squared. So if you let u equal x squared, du would be basically that. So the whole idea is really you let u equal something that's kind of like inside something else. So if I have the integral 4th root of x over square root of x, and then it was, depending on the version, plus 1 minus 2, who cares? Almost doesn't matter what that is. If you let u equal to the 4th root of x, because this is the 4th root of x squared, right? So then that would be like u squared. So if u is the 4th root of x, what is x? U to the 4th, and they can do dx really easy. And u squared would be the square root of x. So that's u. That's u squared, right? And then that's whatever that is, 4u cubed du.
So whenever we get the dx, we just plug it in on.
Exactly. That's kind of the nice thing about when you solve for x here. Dx is easy. Dx is whatever the hell that is. You just put it in. That's why trig sub in that respect, you guys don't even realize this, but that part of it's stupid easy. Because if you let x equal tangent theta, then dx is secant squared theta. You don't have to think about it at all. It's just replace dx with what you just figured it out was, right? That part's easy. Because x equals something. Now, ask anybody in the class, and they'll tell you the rest of this is kind of long, right? But that starts you off. All right, how we doing? Any other questions?
What do you do with the constants? What do you do with the constants?
They just get kind of sucked into this whole thing. You're going to want to long divide. You're not going to want to. You're going to have to long divide. Be careful the words I choose. I don't know if you guys are just nervous about leaving. You could leave if you want to. Or if you have questions, you can ask. Or you can exist in a state of limbo, if you are. Does he mean it? I don't know. Somebody might ask something I want to hear. Yeah.
I have trouble understanding like bounded above, bounded below. Do you need to like?
Very often that question's a little silly, because that last one, and at this point it is a little silly. They just want to introduce the terms to you, really, because later it becomes huge. If you go any further in mathematics, down to proof classes and stuff like that. But that one we did earlier, where we did the derivative a second ago, since the limit of it was 2/5 and it's always decreasing, that would be a lower bound, right? So it's bounded below, just because I could tell it's going to 2/5, right? Can't remember what the some of them are kind of silly. There's one like that. Is that bounded? Sean, is that bounded? Yeah. So bounded above. Let's start there.